Tonight we have a team of 4 people from Carnegie Mellon University, which by the way is my alma mater. I'm class of 78. Okay, and they're going to talk about line clearing robots using a swarm of robots. I'll let them self-introduce their names. Thank you very much.
Mentioned before, we were from Carnegie Mellon in Silicon Valley, and we are doing this. We took a class in architecture and design at Carnegie Mellon. Our professor who co-taught it was Professor Ed Katz. Yay! All right. So I'll introduce Trevor. This is Chris, Shenhung, and Nishin. So this is our presentation on architecture for mine detecting robots. So the agenda for our presentation, I'll just run through it. I'm sure we want the more meat of our presentation, but we'll go over a brief problem description, what we're trying to handle. Then we'll go into our solution overview, just a quick run through of what our solution is. It will be general. And then our architecture description, which will go more in depth at what architecture and our design. And next we'll go into scenario analysis, where we'll look at our architecture under certain scenarios and see how it handles certain quality attributes. Next, we'll cover the potential issues we do have with our solution. It's not perfect, so there are issues. And lastly, we'll cover optimizations that could be made for our solution. So let's say we have 10,000 robots, and we want to give them the task of minesweeping a field. So we want to see how they'll communicate with each other, say, here's a mine here, here's a mine there, how they'll communicate to us to tell us where the mines are. In addition to that, we also believe that there is error with these robots. They may hit a mine, they may blow up. And because we have a set amount of robots, we want to examine, well, what will happen in this case? Because we have a set amount of robots, the other robots will have to make up for this lack of workforce. So what will they do to handle this if a robot happens to step on a mine and explode? In addition to that, we'll have some constraints on our robots. So if there's uneven terrain, it's pretty believable that the terrain they'll be traversing will not be even, it will be straight flat. And because of this, it can offset, they'll be tilted, and who knows, their vision may be offset. And in addition, they'll have limited power. So the communications that they'll have with other robots will not be, they'll not be an infinite communication. They'll have to think about it, how they'll communicate. So they'll have 2 types of communication. They'll have weak communication for close range and a stronger communication for much farther. I'll get into that later, but for the weak communication, we say that they'll only be able to handle 5 communications at once. So that means only 5 communications with other robots. And because of that, we'll put a robot in teams of 5. And in each team of 5, there will be 1 robot that will act as a captain. So each robot in this team will talk to the captain. They'll send its status information. The captain will take this in, it'll process it, and it'll basically be the team captain. So the team captain will then talk to the coordinator for the group. And the group will be composed of 5 teams. So I know this is a little weird. So the group will have 25 robots, 5 teams, 5 team captains. And each group will also have 1 coordinator. So the coordinator will then take the information from the team captains and process that, and will be, of course, in charge of this group. And we also want to put our coordinator in a different group than the team that it's actually coordinating. So that's a little confusing. I'll give an example. So we have team A and coordinator A. We want coordinator A to be somewhere, maybe team C, team F, team Z. It really doesn't matter. We just don't want it to be in team A, because if something happens to team A, it blows up or something, we want coordinator A to still be functioning. So it being in another group will make it a higher chance that it'll still be all right. But in the case that it does blow up, we'll also have 2 backups that exist in other groups, and once this coordinator blows up, these backups, well, one of the backups will take control and take control of the coordination. So every tick, just an arbitrary unit of time, the team captains will capture its team state info, send it to the coordinator. Every 10 ticks, this coordinator will then send its information to the server. So this image right here, I'm not sure if you can see it. It shows it better on this side, is just the team format. So we have robots arranged in these positions, and the reason why is if there's a slight tilt in the field it's traversing, the multiple robots can kind of work together and they'll cover any gap. And in addition, as they go up, as they're scanning, let's say the scanning's not perfect, there will be other robots that will be able to handle the scanning, and they'll, by rescanning, hopefully make for a more accurate picture. Also, as I mentioned, there will be a team captain. It makes sense that it'd be in the middle, but it's randomization, so just to make it more safe. So any one of these 5 robots can actually be the team captain. we have two images here that kind of, the one on the left will be the initial scanning path, the one on the right is the handling of robot dev. So the one on the left is initial scanning path. We can see white squares, and this represents a team. It's fairly simple. These robots in the teams, they'll just go straight upwards in a straight line, just scanning as they go along. But what's more interesting then is what happens if a robot dies. So it is a little hard to see, but the line on the very, very left, it's a blue line, and it suddenly stops. So we'll say a robot dies. If a robot dies, the entire team is discarded. That may seem a little odd at first. We'll explain why we have chosen that later on. But let's say this blue line dies, the robot dies, so this team will stop. The line next to it, the red line, will slowly change its course to handle the red line, the blue line. It'll take over, slowly correct its path, and every line after each team will also slowly correct its path as well.
Now we'll go into the detail of architecture. So, as Trevor mentioned, each team is consistent of 5 robots, and each group consists of 5 teams. And the teams are the inter-team communication is through near-field radio, because it consumes much less power than the far-field one. And there's a lot of information to be sent to some coordinating authority. So instead of everyone sending the information and losing battery power, only the captain of the team would be sending that information. All the team members would be sending the information to the captain, which would then be relayed to the coordinator. The coordinator would be selected. Each group would be given a group ID, and we are using a distributed hash table to select the node whose ID is closest to the group ID. So in a evenly distributed hash table, the coordinator selection would be pretty random, and there is a very low probability that the coordinator will be in the same group as the group which it's coordinating for. So, and the next 2 closest hashes would be the backups.
Just try and make it so we can see in the back. But I can't find the light switch.
Big improvement.
So, in a evenly distributed hash function, the coordinators would be pretty evenly distributed. So, and all the communication from the captain to the coordinator is handled by P2P mechanisms, and there's no connection, no continuous connection. Only when some information should be sent, which is a tick, which could be an arbitrary measure of time, which would be dependent on the terrain, or it could be a distance. So if every robot travels 10 centimeters and the information, or 10 meters based on the terrain, it's a configurable parameter. And every 10 ticks, the information is sent to a server. The server does not play an active role here. The server is only for attaining eventual consistency of the map. So if any of the coordinators fall behind in their map updates, then we are using vector clocks to have a latest map which the server handles. If any of the coordinators fall behind, the server pushes the map to them. So everyone is at the same page. And another piece of information that is sent to the server is when a mine is detected. Because this is a special circumstance, because when a mine is detected, the team stops working. So all the other teams would have to be informed to do the course correction. So this team's area is covered. So these are the 2 important communications between the team and the coordinator and the server. And so these are the group formations. So each group is of 5 teams, and so the small robots on the left, they represent on the right and the left, they represent each single team, and 5 of them together form a group. And this is just an illustration on how the coordinator would be most probably in a different group than the team. So in this case, the team with a star over their head are coordinating for the group on the other side, and there could be many groups in between. So if this blows up, then the coordinator still exists, and he can inform the server that the group has blown up, and they can inform other coordinators that you need to course correct now. So now we'll go into functional diagrams.
Okay, so since our focus here is not necessarily on how the robots will function, it's basically on how they connect with each other and how they coordinate. We went into detail in terms of how the architecture will be laid out. So we defined 2 functional views, one for the robot and one for the server, which I'll describe up next. So basically we can see what components we want the robot to have. We have a communication manager that basically handles all communication near field and far field. We have a mine detection manager that handles a mine sensor that sees if there is a mine in the robot's path, in what he can see of his path. We have an environment manager that basically takes every other sensor. We didn't go into considerations in terms of what those sensors would be, to see what his environment is. Basically, it all contributes to the fact that the path manager is in control of getting this robot to follow the path that has been defined for him. So he uses the motion manager basically to just move along, and the information that the environment manager provides to actually follow the path. Once a mine is detected, we have a mine reaction manager, which is a separate component that, depending on what we want to do, let's say we want the robot to have some type of explosive to actually detonate the mine, or we want the robot to just walk on top of the mine, we have detonation actuators that tell the robot what to do in this situation. So for the server, since the server here is very lightweight, it's not constantly involved in how the architecture is functioning, it's not very complex. So we have an information manager, which is basically, it receives the information for the coordinators that are on the grid and on the field, and provides that information to two other components. Those components are the log manager and the map manager. The map manager is basically in charge of taking the information that has been given to the server by the coordinators and generating the up-to-date map from the information they're getting. And the log manager is basically just a logger. It's in charge of taking the information that is being received and providing it for an analytic system if there is any analytics that needs to be done eventually. Right. So to better describe how our architecture works, we went and did several activity diagrams to describe what we call information views in terms of how the architecture handle certain situations. There's a big document that we can share with you. We did about 5 or 6 of these to handle different situations. This is one of the most relevant ones, is what happens when a robot detects a mine. This is not a robot walked on top of a mine and blew up, but this is actually a robot walked up to a mine, used the sensor and detected that there was a mine in his path. So he tells his captain, I found the mine. The captain sends a confirmation message back and says, okay, I got your message. The captain then relays that information, tells the coordinator for that team, tells him exactly what the status of his team is now. Coordinator says okay, and once that happens, the captain is now not considered part of the grid. Since what we're doing is we're considering that when one of the robots is destroyed or has moved on top of a mine, we are discarding the whole team. This team to which this captain is commanding is no longer part of the grid. So he just tells the robot, destroy, it would be either walk on top of the mine or actually activate the mine, depending on what the situation is. Once that happens, the coordinator also just informs the new status of his group to every other coordinator on the grid. They respond with an OK message. He also sends that information to the server, so the server has a very up-to-date information about what the map looked like, where the mine was detected, and also sends a vector clock to share what this coordinator actually knows to be the map, based on what he has from every other coordinator. So if this vector clock is out of date based on what the server has, the server will not only send an OK message back, but will also send a message that says, well, this is the actual current map, updated based on what you have. Once that, there's an additional path update that every other coordinator sends to their involve other captains, the captains that they are commanding, so that all the robots in the grid have the actual path that they have to take once a mine has been detected, because they have to make up for the room that is that this team is no longer covering. Right. So once we had an idea of what we wanted to do with our architecture, we had to focus on certain scenarios that we wanted our architecture to handle properly. And we did this around certain quality attributes that we wanted to focus on. So one of the quality attributes was scalability. We wanted this architecture to handle not just 10,000 robots, but 20,000, and handle certain situations where scalability was an issue. So we wanted to easily be able to add a robot to the grid, and we also wanted to handle properly when several robots at the same time detect a mine. So when one of the robots, another additional robot wants to be added to the grid. Since we chose a P2P-like architecture and we have a distributed hash table, it is simple to just add a robot to what the distributed hash table represents, and it's basically a circle. We just put that robot in there, and he will be assigned a role if that is what corresponds to him. The only issue we have here is that we can't add a single robot, since we're assuming that we can only add a single team, so we would have to add 5 robots at a time. But that's something we'll discuss in our optimizations. So if several robots detect a mine, our architecture handles that properly, because it's not every single robot for itself sending messages constantly about a status update, but it's very well distributed amongst the grid what happens when one of the robots detects a mine. So it always goes back to the coordinator, and the coordinator is the one that's in charge of steering this message. So instead of 10,000 robots doing this, it would be 10,000 divided by 5, which would be the amount of coordinators that are in the whole, well no, by 25, which would be the amount of coordinators that are throughout the grid. All right, so another quality attribute that was important for us here was consistency. We did not want different coordinators to have different mapped information. So what we did is that we considered that when for some reason one coordinator has different map data than another, we want to be immediately aware of this. So what happens is that every 10 ticks, when you're sending an update to the server, you're also sending a vector clock. So if the vector clock that you're sending is not up to date with other coordinators, the server will return an updated map and say, well, this is the actual map that is now being used. Right. As for availability, it's a huge issue here, where it's a robot carnage. Mines are blowing up. There's robots being blown up all around. And we want to handle this situation properly. We don't want the system to fall apart when a whole group blows up because there was a bunch of mines near them. So when a coordinator blows up, we're fine usually, because first it has 2 backups, and second, it's usually coordinating a group that is not directly in his same group. So if a group blows up, there's a coordinator in another group that detects the fact that they are no longer in the grid, and they can relay that information to the server. And if a coordinator blows up, it just goes to his backup immediately using the distributed hash table. So if there's a catastrophic group failure, like I kind of just mentioned, also the coordinators and backups are spread out throughout the groups. So it's easy to, it's very unlikely that all 2 backups and the coordinator will blow up at the same time, and their group will actually run out of someone to coordinate them. An additional thing that quality attribute that we cared about a lot was adaptability. It's very theoretical, so there's a lot of stuff that, let's say, algorithms that might need to be adjusted, that certain parameters that we might want to change. We didn't want our architecture to be fixed. We wanted to be flexible in that aspect. So that's why we have a lot of separate independent components. So for example, if we need to do a change in the path calculator algorithm as time goes by, it's pretty simple because it is in an isolated component, and the same goes for like the map manager, such. Right. So now we're going to go into some potential issues that this has.
Okay, here are some potential issues we identify in our solution. The first issue is when a robot is destroyed by a mine, then in our solution we will just discard the whole team. That's because when the robot is died, and if we going to reassign the team or the group, it will more battery consuming, and it will cause other issues. So in this case, we just let the whole team be discarded. And the second issue is the far range communication between the captains and coordinators, and as well as the coordinators and the servers. So because we need to transfer the map informations and like the team information, so it will be really battery consuming. So the battery will be our biggest issue. And another one is the false positive. So since it is the real, since it is the real-time situation, so it is possible that we lost some connection with the robot. So in this case, we will just assume that robot died, and that means even though that robot is still alive, we will lose it. And the last issue is the hardware failure. So because we are using because that's the real-time situation, so it is always possible that the hardware will fail. And here are some optimizations. The first one is to save the team. So assume that one robot detects a mine, and then it can inform its captain. So the captain will instruct the rest of the robots to move away from that mine, so that we can save the rest of the robots. And the second optimization is, so once we save the robots, we can reuse these robots to fill in the other gaps, like some other robots detected a mine and then it would just die, and then we use the saved robot to fill in that gap. So we can also add surplus robots following the front line of the robots, and then once some robot dies, and we can use these extra robots to fill in that gap. And so since we are using the far field communication, it is really power consuming, so we can rotate the roles in the team. Like we can switch the normal robot to be the captain and to be the coordinator, so that we can save the battery. And that's it.
Thank you.
Questions? Thank you.
You seem to be very, I guess, cynical or putting a lot of weight in your designs on the batteries running down for radio communication. I was wondering if you have an idea in mind as like what particular technology that you're going to be using that you think is going to drain the battery so much?
We had an idea in terms of like Wi-Fi. Since we didn't go into that much detail in terms of how the hardware was going to be laid out or anything, because at least for this course it was very architecture oriented. So that aspect of the technology we would use was not a factor. We just assumed that, and it was kind of in the proposal we got for the problem description, it was mentioned that it was the technology that you would use for far field was going to be detrimental to battery.
Okay.
It was.
It's a good, very basic assumption, but there are quite a number of low power, long range meshing wireless technologies out there that, combined with some attention to protocol design, I think would give you a much less cynical picture.
No, great, thanks. One over there.
So have you had like do you have like a prototype that's already been built and tested?
No, it was just a theoretical thing it was one of the tasks that we were assigned for a course. So it was a theoretical problem that we wanted to solve in terms of how we would lay out the architecture and how the robots would coordinate amongst themselves.
You may have covered this, but if the coordinator is on a team that retired, but survived,
Okay.
Does that coordinator stop serving as a coordinator function? And if so, or if not, if you make better use of the retired team, since they no longer need motor, you can assume they would have plenty of battery to be coordinators.
Sure. Right, makes sense. But in the cases where, it actually makes I can't find a...
Yeah, it makes sense. I mean, we as we went along with this, we found a lot of possible things that we could improve upon it. Actually, we had a proposed design in terms of instead of kind of covering the field as we lost one, instead of doing that, we would actually reposition the robots that were already on the grid to actually make different size teams, so that instead of giving this guys discarding like 4 robots because we lost one, we would take the one from this one and kind of fill up, and the last team would be, instead of 5, be a 4, and kind of redimension themselves. But we took out the complexity because we wanted to focus on the architecture.
And one of the limitations that we were given was that near-field communication was only able to handle 5 direct communications. So our team size was automatically limited to 5. So the reconfiguration of team was a little difficult. Yeah, but that's a... Please. Yes, sure.
So I was thinking of 3 other constraints.
Okay.
So one of them would be, did you ever consider it might be amplifier?
We didn't consider it.
No.
Thinking of long-term, that's one constraint. The other one I was thinking of wireless interference.
Yes.
In terms of more robust protected network.
We did consider that. Yeah, we did.
Pictures seem to show the coordinator as a different physical size or shape.
No, it is not. No,
Yeah.
I mean, that image might be misleading, but that was supposed to show a whole group instead of a single team.
So you shouldn't be able to pick them out at some point. You don't have to be targeted.
Yeah, no, they're not different sizes, they're the same thing.
Yeah, I mean, so the roles would rotate.
Let's do about 2 more questions.
So, well, I could go on for an hour of questions, but a couple that comes to mind is, what's the whole purpose of the 5-unit? Why are they not just operating independently, autonomously, and just distribute the coordinator, captain function randomly throughout time? Something like the Paxos algorithm would let you form groups of n units reliably, and you could just say every n minutes I'm going to redistribute the network again. We'll find 5 neighbors. So is there some physical reason, like sensor?
Right. So our we were given a low. I mean, the probability of a sensor detecting a mine was not 100% or even close to 100%. So one of the things that we had to keep in mind was that each area had to be scanned multiple times at least. So we thought organizing the robots in that particular shape achieved that goal. But I mean, if the probability of a sensor detecting a mine is higher than that, then I mean they can work independently.
Well, the biggest problem I have in my mind is that once you have detected a mine, you've just lost a huge expensive resource of 5 machines. Whereas they could coordinate together and say, well, once I've detected a mine, let everybody just move away.
Right.
Leave me behind.
Yeah.
That's
That
actually
was actually one of our
optimizations is save the team.
Yeah, that's the first one.
It's pretty much what
I mean, it's stupid to waste all of those robots.
Yeah.
And there's lots of things I could comment about, like the gentleman said about radio communications,
Right.
spread spectrum prevents the jamming effects. Spread spectrum can be used for high power efficiency monitoring and mobile mesh, dynamic mesh.
Auto reconnecting mobile mesh technology.
Yeah, we're running a little low on time. We'll do 2 more questions, Ralph and then David. Ralph first.
Wondering, was your whole evaluation of your algorithm just a theoretical discussion, or did you do any simulations to prove that there were?
This was a complete theoretical discussion, no simulation was involved.
David?
Did you consider the map actually changes each time a robot commits suicide? There's robot parts all over, graders created.
I think we thought about, we discussed
about,
it.
yeah, we did consider, I mean, robots stopping and trying to detect, avoid any collision with the teams that are following that particular team. But since there is a server which detects the current map, and all the coordinators are talking about the maps, so if a team does go down, then that team's coordinator would know about that team being stopped there, and that would then communicate to all other coordinators. So basically, everyone would find out that there is a team standing right there.
Yeah, well, we thought about like
map change after you mapped it.
No, that we have not thought of.
But you mean in terms of a mine detonated and it changed for now there's new obstacles?
Yeah, new obstacles.
Well, I think it would basically, if a team is moving along and they're detecting that there's an obstacle, I guess the team would handle it and then update the other coordinators and tell them that there's been a change in the map. And so since there's a constant update of the map, it could handle that properly. There's not a predefined map.
Yeah, we clearly have more questions, so after the next talk, you can find these gentlemen and ask them questions some more. We're just a little tight on time here, so thank you very much.